The reason for this is that by probabilistic constructions it is quite easy to provide examples or models where strong local dependencies occur, but still you have some kind of asymptotic independence. Of course, those local, strong local dependencies, they influence the form of parameters of the limit. When there exists variance, the second moment, then of course we can manage with those local dependencies in a relatively easy way, of course. While in case of really heavy tails, it is not easy. Also, in case of really heavy tails, the dependent structure is reflected in the form of functional limit theorems available. I am not aware of ergodic theory, of methods of ergodic theory that can help in this respect. I hope after this workshop we will know something more. The story began in 1957, so it is customary at this point. We had some references to the deep history of probability theory. It is also the case. Because we will work with stable distributions, let us recall the minimum of knowledge on this topic. Suppose we are given IAD sequence which with regularly varying tails, and tails which are balanced according to some constants. We will always assume when such model will appear, Yj will be reserved for IAD sequences, that we have centered situation if alpha is bigger than 1, and we have symmetric if alpha is equal to 1. Then it is one of basic limit theorems after central limit theorem of probability theory that after suitable normalization that can be found by solving implicit asymptotic relation of this type, with this normalization we can obtain strictly stable limit. Since there is we do not consider centering, which is always possible, not always, in case alpha different from 1 is always possible to reduce to strictly stable limit. We will assume that Z is strictly p-stable. This will be denoted this way, where here it's a Levy measure, which is specified, of course, by the power, by the exponent, and those two constants corresponding to jumps, to the positive jumps and negative jumps. So we have standard limit theorem for independent random variables, identically distributed random variables. What Skorokhod did in 1957 was to show that those random variables are convergent not only to one single, but also this in distributional manner, where we equip the space of trajectories. Clearly, those stochastic processes, they have Cadillac trajectories. We can equip this space with Skorokhod topology introduced by him in a paper older by 1 year. Then we have this convergence in distribution, that means in functional manner. Two things are relevant here. We have to remember always that these are two different papers, and I can tell you a story related to this fact. 3 years ago, I participated at some conference devoted to stochastic analysis, and there was a speaker said, by corollary 2.61 of Jakubowski and Shiraev. And I would like to stress, it is not corollary to 0.6.1, but it is a Skorokhod theorem, one of most important Skorokhod theorems. So this is the, of course, often forgotten, but result of Skorokhod from the paper in 57, which was devoted to a functional convergence of processes with independent increments. What was the J1 topology? Because we are going to deal with several topologies, I am trying to make some short overview of 3 of them, and about J1, which is of course most important, because it is the strongest one. We consider Skorokhod space, that means space of Cadillac functions. Of course, we can consider on this space the uniform norm, and it is a Banach space with respect to this uniform norm, but of clearly non-separable Banach space, which causes, of course, always problems in probability theory. What is J1 topology? The idea is that we allow time shift, and this time shift is provided by taking some homomorphism which are continuously increasing, preserving 0 and 1, uniformly converging to identity. Then after slight time change, we should obtain uniform convergence to the limit. So this is a relaxing of uniform convergence, weak enough that it is still provides strong results, but it is not with this topology. This is a metric topology. In fact, we can easily define metric corresponding to this convergence. With this metric, Skorokhod space, space of Cadillac functions, becomes a separable metric space. So we have some proposal. Of course, this definition is well known. I just recalled it for completeness. In the original paper, when Skorokhod introduced, this was related to Heisenberg principle that we cannot describe the position and the time at the same time. But of course, this was just some publicity, I guess. We have some further results. This metric is not complete. Billingsley was able to construct a complete metric given by explicit but not easy to calculate formula. Equivalent metric which converts space D into a separable and complete metric space. What is moreover, it is possible to prove that the Borel sigma algebra generated by J1 is simple. The sigma algebra generated by projections, by evaluations at point T. PT is evaluation at point T. And because of that, simple every stochastic process with Cadillac trajectories has a tight distribution on D, because exactly this is guaranteed by the fact that PT is that of the structure of the sigma algebra. So we can work quite easily, and this was the reason for great popularity of this J topology. The drawback is that D itself is a linear space, but D with J1 topology is not a linear topological space. That means the addition is not continuous. And the standard picture related to this fact is as follows. We will see this picture 3 times during the lecture, and every time there will be different meaning of this picture. The picture says that suppose we have a sequence of functions fn which is convergent to function which is described with unit jump at 1/2. And of course this jump is shifted a bit, but when n tends to infinity, we clearly see that there is a slight time change that allows us, after this time change, uniform convergence. Similar way, similar phenomenon can happen also from the right. But if we subtract those two functions, we obtain something that cannot be cancelled by any time shift. Therefore, we don't have this sequence, this difference cannot be convergent in Skorokhod sense, in J1 sense, to the limit, which is clearly 0, because this is self-cancellation of the jump in the limit. So this is a standard picture. It does appear in almost in every book where there is more words about Skorokhod topology. What is important is to realize some properties. First, if t is a point continuity of the limit, then of course also we have a point of continuity as a Cadillac mapping. Then also evaluation is continuous. If the limit is continuous, then we have the J1 convergence is equivalent to uniform convergence. Evaluation is J1 continuous if and only if T is a continuity point. Moreover, we have always, if Xn converges in J1 to X0, convergence pointwise outside of some countable set, which is the possibly empty, but of course we have this guarantee. And this is the most important thing, sorry for jumping too fast. If Xn converges to X0 in J1, and in the limit we have a jump, this difference is non-zero, then this jump is approximated by jumps at possible different locations, but tending to T0, of approximately the same size in the sequence approximating X0 or tending to X0. So this is the one to jump. This is the principle of J1 topology. Yes. In establishing convergence in distribution on the Skorokhod space in heavy tails models, of course, when we have independence, we can use different tools. For example, the original Skorokhod theory. But if we pass to dependent situation, then the most important tool seems to be point process methods, and the principle is quite easy. We have a partial sum. Sorry for different normalization in this picture. We had an before. If we have a partial sum, then we can represent this partial sum as the integral with respect to some random measure, which is simple, given by in the following form. So we have a representation of the sum as the functional, linear functional of some point process if we have a if those point processes are convergent in distribution to some limiting point process, then we can expect that there is a convergence of the corresponding sums. The point is that if n infinity, the limit, is a Poisson point process, then under some additional conditions, it's of course, but of technical nature, we obtain also that the process Z and T converges to the limiting process on the space D and D equipped with J1 topology. So this is, of course, it's a result, it's a serious result. For the first time, this idea was used in application to dependent case by Darrett and Resnick. We shall see in a moment this reference, but here I would like to stress, because of the property of J1 topology, which is jump to jump, it works in case of point process when the limit, namely the Poisson point process with non-atomic intensity, is a simple point process, namely there is no multiple points, and this means that if we have a limiting point, there is some limiting point, but only one approaching the limit. And this is the reason for the J1 convergence produced this way. Darrett and Resnick in 78 used conditional versions of standard assumptions of convergence of point processes generated by independent sequences, and they proved such functional limit theorem using this way. It is interesting, and I would like to propose you some simple method which is related to so-called principle of conditioning, and in fact it is contained in martingale approach in very general manner. You can find it in the paper from 83 by Jakubowski and Memel. And the idea is that, but in sums, in case of sums, you can do that much easier. Suppose we have a sums processes built upon sums of random variables. In each row, those random variables are adapted to some filtration. Consider characteristic functions, conditional characteristic functions, which are obtained by taking x and j with respect to the past, the conditional of this function with respect to the past, and then let us consider the function which is obtained by product of those characteristic functions, conditional characteristic functions. They are, of course, random variables. The principle of conditioning applied in this case says that if for each theta those characteristic functions, here it should be phi n of t, of course, converge uniformly in probability to the limiting characteristic functions of the process with independent increments, which is continuous in probability, that there is no fixed points of. Then, on Skorokhod space equipped with J1, we have this convergence. And of course, it is clear that this is a technical condition, but it can be obtained. We know what to do. It can be obtained in terms of conditional truncated expectations, variances, tape probabilities, and so on, as it happens in martingale limit theorems. In particular, if node centering is involved, then we obtain only from pointwise convergence, because the characteristics in the limits are continuous, and we have cumulative characteristics which are non-decreasing. Therefore, this is implied. This implies uniform convergence. So then, using Aldous criterion, it is easy to show functional convergence. And in particular, we can consider so-called stochastic volatility model, which is quite non-trivial, and still people in econometrics, they try to do something. Suppose we have a innovation sequence which is independent. This is the independent random sequence, but the volatility is a stationary, ergodic, and predictable with respect to fj. That means it is measurable with respect to the prior function. We know there are many such models considered in econometrics, at least, because this says we built it on the available knowledge. We have with this model, which is with strong structure, but not completely obvious, especially when we deal with heavy tails. We can, under natural assumptions, we can show that the products of characteristic functions using, in fact, ergodic theorem, this is important. We can show that we have this pointwise convergence, and by stationarity, this transfers to the uniform convergence, and therefore we have a functional convergence of sums of stochastic volatility models, and this gives some functionals that can be of some interest. In particular, suprema are convergent. So we have the full power of convergence to Levy stable motion, preserved from independent case to models of this type. I would like to advertise a talk by Marta Tyran-Kamińska. She was able to provide the necessary and sufficient conditions for J1 convergence of stationary random variables. This is a paper from Stochastic Processes and Applications, and at the same time she was able to examine those conditions in context of stochastic models built in terms of measure-preserving transformation, therefore, or dynamical systems. I hope it's my initiative that her talk will develop those ideas. Therefore, I am going to review some functional limit theorems where J1 convergence simply cannot hold. And it is not necessary to go too far to find models which exhibit some clustering of big values, which also for which we cannot prove J1 convergence. Suppose we have as before, but of course it is not necessary to restrict on the IID sequence, and we build usual linear processes on those innovations. Of course, we have to assume conditions guaranteeing that on the coefficients, so that this series does exist in low or in almost surely it's equivalent, as we know. What is important in this case, that this model propagates big values. If some random variable takes big value, then of course in all other places with relatively big coefficients, these big values still appears. Of course, in case of central limit theorem, this is not so clear whether really big value will occur in some other place, but in case of innovations with heavy tails, we know that it is mostly from time to time a very big value, and therefore this phenomenon can be clearly seen. Well, there is a paper by Mikosz and Samorodnicki published in a long time ago, 14 years ago already, but they do some simulations. They analyze the situation, whether we can use such model, such simple model, in analysis important from the point of insurance companies, because the clustering phenomenon of clustering of big values is well known, especially to those where we know that catastrophes do not go alone. There are always some coupling. There's always some coupling, and so on. So it's this paper can be recommended as a source of at least analysis. I don't know whether it's convincing or it is really cannot be questioned, and so on. Nevertheless, such models were considered by them, and of course by many other people later. In order to formulate some result, we need to solve our problem about existence of the series of the linear process, and it is quite easy. Suppose we have this tail property. This means simple that this random variable does not belong to the domain of attraction. It simply has regularly varying tail, and the question under this assumption, the question of convergence of this sequence is equivalent, basically under our technical assumptions, is equivalent to convergence of such a sequence where h is the function appearing in the tail. So clearly, it is not enough that this series converges. Sometimes we can need more, because the tail is different. Yeah? So, of course, this is a simple, just produced for completeness, and then, assuming this fact, we know that this series is well defined, and we can ask, therefore, about convergence of suitable normalized functions S and T. And of course, this is not a new problem. This problem was intensively studied in 80s, and some of people obtained quite satisfactory results of Strauss-Kass and Kasahara and Maejima. They showed that in general fractional stable Levy motions can appear in the limit, and some of the limiting process can have continuous trajectories. Some other have trajectories which are unbounded on every interval, so useless from the point of view of analysis of limit theorems. But this is a general theory. We are not going to develop this idea. We shall concentrate on some very special but quite important assumption where we have the coefficients are summable, and for this time on, just to avoid some complications, let us assume that P is bigger 1. Then the series under this condition, the series is well defined, and for such series, in this particular case of Strauss-Kass and Davis and Reznik using point processes, and also the mentioned paper by Kasahara and Maejima applying integral representations, they were able to show the following theorem. Under our assumptions, P is between 1 and 2, the coefficients are summable, and the numbers are taken from our original convergence. These are innovations, and we know those innovations under normalizing by AN are convergent to some strictly stable distribution. Then this sum, the partial sum process built upon those sums of linear processes with the same normalization are convergent in distribution, but in the sense of finite dimensional distributions only, to the T where this constant A is a sum of those constants. We have summability of this, therefore we can write down this sum. It does exist. And of course the limiting process is again the p-stable Levy motion, the same as in this case built upon this random variable when T is equal 1. So we have some finite dimensional distribution, and it appears that in this case we cannot make this convergence stronger in case of M1 or J1 or M1 or any of Skorokhod topologies, because in all those Skorokhod topologies the supremum is continuous at least at points which are points of continuity of the limit. And there is a very simple example. This is self-canceling example, namely if in our linear process we take all Cj's 0, but we have 1 and minus 1, so then we have something that people in ergodic theory call yes. And of course simple self-canceling sums, and it is not surprising that we have because this sum is equal to 0, we have convergence to 0 for each T in probability, and on the other hand, if we take supremum of SNT, this is equal to maximum of random variables which have heavy tails. And such random variables with heavy tails under the same normalization, they are convergent to some Fréchet distribution. This is well known from and easy to compute from limit theory for extrema. So supremum is not continuous because the limit is 0, so it should be convergent to 0. So this is our consequences. So this means we have no in general, we cannot expect that in the general case, we cannot expect convergence, functional convergence in Skorokhod topologies. In this example, the limit is degenerate. And therefore, some people say, well, so perhaps we can choose another normalization such that there will be not this bad phenomenon. In fact, Avram and Taku showed that if at least two coefficients among Cj's are non-zero, then SNT is not uniformly tight in J1 topology. So this is more, it's not only our example before, but it is possible not with two particular coefficients, with very special choice of coefficients, but in general, if there are two non-zero coefficients, then SNT is not uniformly tight in J1 topology, and this is because of violation of this idea that one jump to one jump. But they proved something instead. Suppose all coefficients are non-negative, and it is original assumption of Avram and Taku. Both sequences are monotone, of course tending to zero if they are assumed summable, plus some technical conditions, very popular among people using point process techniques. Then those processes which are built upon positive coefficients, but of course they are not, those sums are not increasing. The random variables are quite arbitrary. They are convergent on the Skorokhod space D equipped with M1 topology, so-called M1 topology. And let us say a few words about this M1 topology. What is the difference between J1 and M1? Because this is much less popular topology. But in many respects, there are more and more papers appearing. When you look, it is not very intensively investigated topic, but more and more we know about these things. As before, we have a Skorokhod space. Xn converges in M1 if there are parameterizations of extended graph. What is extended graph? If we have our standard example, say something like that, this is the model of Cadillac function. The extended graph means that we join ends when jumps occur. And then we obtain a continuous curve in the plane. And therefore, we can parameterize it. And then after taking suitable parameterizations, we will say that Xn converges to X0 if both parameterizations are convergent and also uniformly the functions. So we have some kind of, okay, even a metric. Then, of course, we can prove, it is possible to prove that J1 is stronger than M1. And what is crucial for investigations, this is not well tractable quantity because there are too many parameterizations and so on. It is not easy to compute. It is much more instructive is the fact that we have this is people familiar with functional theory, you know. There is a modulus continuity corresponding to M1, and this modulus continuity is expressed in form where we have a distance between the point in the middle of the trajectory from the interval between with ends in x t1 and x t2. So we have something like that. We have some jump, and we wish to have that the limiting function is close to this jump. Here is the graph, extended graph of the jump in the limit, and we see when we put the interval this way, it is approximated in the sense of M1 topology. So we have some tool to investigate this M1 topology, and all other properties are the same. More or less, this is a losing space, whatever it means. This is simple that there is a stronger Polish topology than the usual properties. But similarly, as in the case of linear space, it is not a linear topological space. And, okay, again, we have this example. Because we cannot parameterize any parameterization we will take for this extended graph, there will be no uniform limit after this parameterization to zero. So we have, again, we show that this example is good also for M1 convergence. And we have standard properties of pointwise convergence. What is important here is the fact that if we have xn converging in M1 to x0, and we have a jump in the limit, then we cannot say anything about xn tn, except for that it is close to the interval built from x0 t minus and x0 t. So exactly this case that we know if we approach t with tn, xn tn must be close to some point in the interval. We can prove much more about M1 convergence, and there are some other results prior to this paper, but this is very general in his form. For example, if we have a stationary sequence of associated random variables, I'm sorry, I will not explain this in detail because this is, of course, this is a generalization of positive correlatedness, but quite special. And if we consider this convergence in finite dimensional distributions, then we obtain convergence on the Skorokhod space equipped with M1 topology. So if we add to our setting that those random variables are associated, then we obtain convergence in M1. This is quite general. Of course, this is more general. One can say this is proving that Luigi and Rio, they prove only tightness. But as I said, tightness in M1 is hardly tractable. There are no easy, as in the case of J1, criteria of compactness for M1 topology. So after Luigi and Rio, we can say if all Cj are non-negative and the coefficients are summable, then we have convergence of linear processes on the Skorokhod space D equipped with M1 topology. So we have now, without any technical additions, we can say this theorem holds in full generality, in natural way. Of course, we can also consider P smaller than 1. In this case, this condition implies summability, but convergence of finite dimension distributions may require some different norming than an. P equal 1 as always requires special attention, so we will not discuss, because our aim is to provide models where several topologies appear. One can say that one can prove similar results for iterated monotone random Lipschitz maps. And this is quite a recent result due to Mirek from 2011. It is he adapted some ideas of Letac's principle, well known in France especially. Suppose we have a mapping which is random, depending on some coefficient C, and our assumption is that with omega fixed, this is non-decreasing and Lipschitz, with some constant depending, of course, on A epsilon. Then if we take independent copies of such a random map, and in addition we put some independent random variables, then we obtain a homogeneous Markov chains by this iterating. And because of this property that this is non-decreasing function, we obtain that those random variables are associated random variables, and therefore we can apply Luigi and Rio result. This is additional remark only that, of course, for this Markov chain, we have enhanced tools for checking existence of the unique stationary distribution, and this is distributional solution to this equation where with psi and r, capital R, independent. All this is well known in the area of arch and gauge processes. And arch processes are well known in econometrics again for 30 years. Even Nobel Prize was given for modeling using arch and gauge processes in 2003. We see that if we take this is x, and this is something responsible for omega. So this is not a monotone distribution, but if we consider squares of zsk and we consider this recursive formula, then we obtain, after simple manipulations, we obtain the formula which is already, this is non-negative, this is increasing in x, therefore it is a monotone Lipschitz map, and this is a good example, and therefore by Luigi and Rio obtain M1 convergence of squares of arch1 process, of squares of arch1 processes, but not for arch. So not for arch because this is not a proper. I recommend this paper. It is quite efficient, and many models can be constructed on the basis of this paper. One should mention at this moment also another approach to M1 convergence. So far we had standard thinking. Finite dimensional convergence plus tightness gives us functional convergence. In this paper, a somewhat different method is developed, namely they adapt the method of point processes in the sense that they restrict the action to some subset of point processes with good properties. Their assumptions involve so-called tail process, which is simple the limit in the sense of finite dimensional distributions of this sequence rescaled and conditioned on x0 bigger than x. So this tail process, really clearly it is tail process because x is assumed to converge to infinity in this case. The assumption is the tail process almost surely has no opposite sign. That means they look the same in the limit. And they are able to provide stationary sequences with this property, but which are not associated. That means this is more general theorem. But still, arch1 processes do not seem to fit this formalism. So, despite this is a relatively new result, still classical arch1 convergence do not fit to this formalism. So, okay, I'm close to the end, so let me mention only two things. First, the conjecture by Avram and Taku. Still holding, not easy to be proved, I guess, because it is on the space, on the topology M2. If they assume that if we have this property, that means all are non-negative and there are not jumps below zero when we analyze such processes, the partial sums to the whole sum. So they allow some negative, but they do not allow to go below. Then they suppose that it is convergent in M2 topology. And this time M2 topology is very simple to define, namely, if we have two Cadillac functions, we take extended graphs of those functions, and we take the familiar Hausdorff distance between those extended graphs. It is likely that this conjecture is true. Of course, it is probably not the most important, but it is interesting and also a computational challenge. As I said, if we take one or two coefficients, it's easy. But if we take all of them and we allow that they do not vanish, it is not so easy. It does not seem to be easy. What can we say about M2? It is weaker than M1, but is incomparable with S topology, which I'm going to introduce next. No, this is about functional convergences. So there are J1, M1, M2, S topology. We mentioned this example showing that this example in general case excludes all Skorokhod topologies. It is possible to show that this, if we take those two things with C0 plus C1 bigger than 0, then this sequence Xj is not tied in M1 topology. So we cannot hope that, like in case of M2, this is still open, the conjecture by Avram and Taku. But in this particular case, we have a simple example of the conditions preserving the power, but it is not tied in M1 topology. Thus, we have to switch to S topology. And we did it. I mean, without assumptions about Cj, only summability, there existed topology on D01 defined long time ago and for different purposes, such that the linear processes converge in S to this limit, equipped with this S topology. And the idea is, in this particular setting, is very simple because we have in hand some powerful tool, namely the computation, the tightness by Luigi and Rio. Decompose random variables. Let us see, this is misleading somewhat because it does not mean this is the positive part of xi. This is the sum with positive coefficients only, while xi minus, this is the sum with negative coefficients. We can, of course, then decomposition, and this is convergent in distribution under M1. This is convergent in distribution under M1. So we have a difference. We know that M1, it is necessary to prove M1 is stronger than this S topology, and we know S is sequentially linear. It does not mean continuous. So this is, as we shall see in a moment, S is not metrizable, therefore it is delicate to manipulate in applying continuous mapping theorem. It is not so easy. We need some going through Skorokhod representation. So this is the general idea. As I said, we use the convergence on M1 in M1, and one of applications is which I cannot obtain this convergence without this functional theory. This convergence says that we have, in fact, we can replace our linear processes with converging in Skorokhod manner, but in this particular sense, not uniformly. There is no chance for uniform convergence, nothing like that. I cannot obtain this fact directly. And one remarks only, the proof was heavily dependent on the result of Luigi and Rio. It is possible to prove S tightness directly, and also we are able to prove this way, using this general method, that sums of Arch1 and Garch1 processes are S functionally convergent to stable Levy motions. So to finish the talk, it's only one word, one slide, say. S topology is the only sequential topology on D for which this topology is defined somewhat different manner. It is not metric topology, it is sequential topology defined by criteria of relative compactness. We say K satisfies two conditions, namely it is commonly bounded, uniformly bounded over all K, and we have boundedness of number of upcrossings of arbitrary two levels, or alternatively boundedness of number of oscillations. Those conditions are two conditions on K. They were used a long time ago, but it was proved in 1997 that with those conditions there exists this S topology, which is the only sequential topology guaranteeing the fact that a set is relatively compact in this topology if and only if it satisfies so easy to check, especially when we use martingale method conditions. So let me stop. I can say that, okay, this is a good opportunity. There is a paper from '97 in Electronic Journal of Probability devoted to this S topology. And that's all. Thank you.
Recorded also. Are there any questions? Okay, maybe I should kick off with the question. So this is a whole range of topologies. Is there any hope to get rates of convergence or bounds on the distances with any of these?
Of course, I know results in general, for example, approximation of semi-martingale theory, where you get a rate of approximations of the order n2 minus 14 or something like that. It's, sorry, 1/14. So this is, in general, it's my impression that in such models, passing to the limit helps us in understanding what's going on, what can we expect, what phenomena can occur, and the rate of convergence, I think, are the secondary importance. Simulation that we know that something stabilizes in the limit. This is the philosophy, I guess, in case of convergence to, especially for dependent random variables, in case of convergence to stable Levy processes or Levy processes, and so on. So this is not, of course, also some results of the type, because when we establish some functional convergence, we can have hope, and this hope is justified, for example, to have some convergence of functionals of the type of a stochastic integral. It is necessary to realize that given functional form of convergence, we can obtain some convergence of stochastic integrals, not only some functionals, direct functionals of our stochastic processes. So this is the reason for studying such things.
Continuing the previous question, talk about strong invariance principles. So here the question is whether one can consider also strong. I mean, there is this general Skorokhod theorem that you can consider some space that if you have weak convention distribution, then you can get almost sure convergence on some big probability space. The question is whether you can get some estimates of this convergence. So there's strong theorems in these Lewis settings.
And so I think that strong theorems require strong assumptions in a sense. So of course, for this S topology, for example, the main tool is Skorokhod-like representation for subsequences. That was in a bunch of papers published parallel in Teoria Вероятности и Opimienia, 97. And this Skorokhod representation for subsequences is applicable and somewhat unexpectedly, because people would expect that to have a Skorokhod representation you need strong results, strong assumptions like completeness, and so on. No, you can have such a Skorokhod representation for subsequences or with the only assumption about submetric space or existence of a countable family of continuous functions separating points, which is very weak assumption, which is very extremely weak assumption. So this theory developed for S topology is paralleled by some theory about general functional convergence suitable for topologies which are sequential, for example, and not metric. So this theory does exist and is used. It is, for example, to finish the comment, for example, everybody is familiar in this room in ergodic theory, among ergodic theory specialists about weak topology in Hilbert space, for example, in L2 weakly convergence sequence. So it is possible to, using this theory, to provide a Skorokhod representation for weakly convergent sequences of random variables in distribution weakly with respect to weak topology. Thank you.